Hello, everyone, and welcome to week 4 of climatology. Just on, yeah, we're kind of wrapping up our sections on sort of the theories. So we have just a couple more weeks of sort of the background science behind it, and this is the one of the first weeks of really digging into that. So we've had a couple weeks of kind of thinking about the data that we use. Now we're getting into the science and the theories behind the our understanding of climate systems for the next few weeks, and then we'll finish out the term. So we're kind of entering the second module of 3 weeks, right? And we'll then finish out the last 3 weeks, talking about the sort of the outcomes, the models that we've built, and the predictions that we have, and everything. So this week it's all about theory of climate, climate science, the theories that drive the climatology and climate science that we discuss and we understand. And a lot of that centers around energy budget. But first, fun fact for the day. So this is, again, another map from my buddy, the climatologist. And as we all know, we just had a change in administration. And so he generated a map. So those are not arbitrary dates up there. He generated a map showing what the departures were, the average temperature departures from normal were for the 4 years of the previous administration. And he didn't go into the details because this is largely done as just a funny kind of map. Why not pick some arbitrary dates and do a slice of climatology? So he didn't really discuss whether or not he compared this to the 1980 to 2010 normals or the new 1990 to 2020 normals. But either way, it's fascinating. And there's actually a little bit of logic and science behind why you might want to do something like this. Oftentimes in the understanding climate change, communication, and climate sociology, which is this new subfield, right? Um, People say, oh, but you can't expect folks to really have a good working knowledge of things beyond the most immediate times. And so analyses like this can actually tell us a little bit about what was the sort of overall feeling about climate, or what was the climate when we were having this this period of an administration. And so this is temperature, average temperature departure from normal. And you'll see that, for the most part, we were warmer, though the north, well, just the northern US, basically. Certainly the Midwest, northern Midwest, I guess, was cooler than average, as kind of shown by these light blues and whatnot. And you can see this grid average. So this means across all the stations, there was an average of 1 degree Fahrenheit warmer than the climatological average. So this is the average of 4 years compared to the climatological average, right? So that's pretty interesting, right? And you see some fairly extreme ones, and if those happen to coincide with like highly populated places, you might expect then at that during this 4 year period that there might have been more climate awareness or something like this. He did it also for precipitation, all right, which is really cool, and this is one that I think potentially gets society or get people kind of more motivated and more anxious about future climate, or just climate realities in general, is when you either have too little or too much, which is basically the West versus the East, right? The West has had too little, largely. We got a few stations in Oregon that are okay, but for the most part, we've seen a reduction of at least 75% of normal over just that 4 year time period, right? But then in the East, we have these belts for sure that have gotten quite a bit. But largely in the Midwest and East, it's sort of right on par, percent of normal in terms of precipitation over the last 4 years. So anyway, random fun fact for the day. All right, so we're talking about climate science and the science behind climatology, and which is really a synthesis science in itself, right? Most of environmental sciences are synthesis sciences, meaning we're building off of what other sciences have demonstrated. We're talking today largely about physics and chemistry, right? This is the reading you did, chapter 4. and thinking about the theory of climatology, or behind theories behind climatology. But so we've got this system, right, of forcings and feedbacks, and the book kind of introduces you to those terms, right? So forcings are the things internally within the Earth system that that really, well, no, sorry, forcings are the temperature inputs, and feedbacks are the things that happen within the Earth system, right? That can either feed into more forcings or absorb energy and that sort of thing. But it's good to remember, just this is our conceptual understanding of climate, right? And remember, the book talks about the first law of thermodynamics. And this is important in this context, because when you look at this, you have to say, okay, this is a closed system. So energy is coming in and it's being passed around and moved back out, and some of it's going back out, but it's not being created nor destroyed, right? It's just being shifted from one thing to another. So this is a closed system. And that's really, really crucial, because that's when we start thinking about these energy budgets, because we can assume that we are these closed systems. So everything that comes in has to match whatever is coming out, or at least in an idealized state. And if it's not matching that, then you have to measure what's causing that change. So energy is neither created nor destroyed, right? So this is, so a change in some sort of energy, and this is over time. So any changes over time have to be explained by inputs and outputs. That has to be sort of matched. So we think of this as a fixed thing, and so you might have inputs changing, but if you have inputs changing, then the outputs have to change as well. And that's really what it's coming down to. So you don't really need to, know these equations outside of, okay, this is a balanced equation, right? Which means you can flip it around. You can kind of ask questions about, well, if we do see an observed change in this, then we can calculate it by looking at what was the initial condition. So say this is, temperature in 2050, and this is temperature in 2010. So the 2050 temperature has to be the 2010 temperature plus any inputs over those 40 years minus the outputs, for those 40 years, times the change in time. That's how we figure this out. That's how we balance out the energy budget. So in order to kind of start plugging numbers into this energy budget, this idealized energy budget, we have to start thinking about what are our inputs? What are the I's? What are their inputs coming into the Earth? And you already know that the sun is the biggest, and the sun is giving us all this solar radiation across all kinds of wavelengths. And so that's where we need to start, is thinking about, okay, well, what's coming off the sun, and how much energy is contained within this. So this is all stuff going back to Einstein, right? The fact that we understand the different particles have different properties in terms of how much heat or energy they can store and transmit. And we know that stuff down here transmits a lot more energy than stuff out here. So these are low energy, kind of long wavelengths, right? Stuff that moves real slow. I mean, like 100-meter wavelength lengths, right? Measurements between here and here. 100 meters it's huge, right? So really slow kind of stuff that requires very low energy versus, X-rays and gamma rays, the things that, microwaves, all that kind of crazy stuff, right? That it's just really, really, really intense. It just holds a lot of energy. And hopefully most of you kind of remember this visible spectrum stuff. Those of you in remote sensing, this should all, or who have taken remote sensing, or even just maps and cartography, should remember a little bit about this, that we have the visible size slice, which is just a teeny little bit of the electromagnetic spectrum. Although it is on this threshold between like super high energy wavelengths and reducing wavelengths, which is interesting and part of how the Earth systems have evolved. So we've got this whole range of solar and radiation coming our way. And what we need to think about then is, okay, well, what's that radiation doing? So it hits the atmosphere, and what does it do? And so the book goes into a lot of this black body hypothesis or theories, right? The science behind black bodies and these perfect black bodies. And really, like, the best analogy is what we've just had this week, which is snow. And when we have snow on the ground, especially at this latitude, now this is typically what we see. We see pavement relatively clear, and we see snow collecting on the grass and, other surfaces that aren't black. And this shows the black body concept very well. So this black, and you all know this, absorbs the solar radiation incredibly well, like incredibly well, right? Almost as well as water, actually better than water a little bit. So the book mentioned the emissivity of ice and water is 97, 0.96, 0.97. So really, really high, almost a perfect black body. Well, roads are even a little better than that. They absorb a ton of energy. And because of that, they are able to melt off snow a lot faster than, say, dirt and grass and trees, even though trees have darker pigments, they're still not this black body. They don't have that potential for storing all that energy like the black asphalt does. Some of that has to do with chemistry. A lot of it has to do with color. It's the fact that it's not reflective. It's absorbing. So we have this radiation coming in, and the black bodies, the darker body things, are absorbing it and then not releasing it back off. It's not reflecting that back out into the atmosphere. It's really just absorbing it. Versus over here, that's not absorbing it. Snow is still absorbing some energy on some wavelengths, but it's largely bouncing it back out, right? And that's the albedo effect that the book was talking about. Things like silver and aluminum foil that are super reflective have just super, super low emissivities. So they're not absorbing very much at all. And so the book kind of put out this figure, right, that talks about just comparing the relative amount of energy that the sun puts out. So this is a logarithmic scale, and comparing it to the Earth's energy output. So when we have these black bodies and all these surfaces within the Earth's within the Earth or on the Earth's surface, are sitting there and absorbing some level of energy. All this stuff, right? It's absorbing some of it. But when it's not absorbing it, or what it doesn't absorb gets reflected back out. And this is that energy output from Earth. So this is the stuff kind of coming back off. So you have the initial energy coming down, hitting the snow and bouncing back off because not a lot of it's being stored. So you have a little bit of this far infrared in the bounce off, but actually the far infrared mostly comes from those black bodies that are sitting there absorbing it and then slowly radiates it off into the Earth's atmosphere or into the air temperature, basically. But it's not nearly equivalent to what the sun originally produced, right? So it's like sixfold, I believe, is what the book was saying, right? Sixfold difference in energy output between what's hitting us at the top of the atmosphere versus what we're reflecting back off, or radiating back off, not reflecting, radiating back off into the Earth's atmosphere from the Earth's surface. So, and they kind of talked about this energy balance. So if you're to take that kind of data and plug it in, you've got your incoming solar radiation, and we're not talking about vegetation yet, right? We're just talking about bare rock. Incoming solar radiation, about a third of it gets immediately reflected back out from albedo and clouds. This is why it's so important to have snow cover and clouds, because a third of it bounces right back out simply because of that. Then you have some absorbed radiation based on the black body concept. So we can measure, the absorption of all kinds of materials on Earth. And then we can estimate how much would be emitted back off of that. So we have the absorbed radiation, and then we have the emitted terrestrial radiation. So once that road has absorbed all that energy and it starts emitting it back out, we can measure that. So that's one way of doing this energy balance model. But hold on, there's more, right? So we've got all this energy coming in. This is just that electromagnetic wavelengths again, right? We've got all this energy coming in, but it's not even. And actually, our atmosphere kind of filters out a lot of it. so it doesn't hit the Earth's surface. So it's actually really only parts of the electromagnetic spectrum that's making it through the Earth's atmosphere and hitting that Earth's surface. In remote sensing, this is what we don't see. You know, we only see the stuff that's hitting the Earth's surface bouncing back up because, well, if it's not bouncing back up, then we can't take a picture of it. It's been absorbed. There's no more energy and being emitted off of it. We can't, or reflected off of it. We can't take a picture of it. So we have this kind of curve showing, so a ton, right? A ton of energy is produced at those lower wavelengths. But a lot of it does get sort of filtered out. So the red is, well, let me see, top of the atmosphere. Oh, at sea level, how much gets absorbed. So you can see that you know, a lot of it is being dealt with in the atmosphere. And then you get these little dips and everything where the atmosphere is really doing the most, and only certain amounts are kind of hitting the Earth's surface. So what does that mean? Well, it's really interesting, because then you start to tease out, okay, well, this is all the energy coming in from the sun and hitting the top of the atmosphere, and some of it's making it down into the Earth's surface. And you see here how much is being sort of absorbed. So this is kind of the inverse of here, right? This is the amount being generated or broadcast from the sun, and the UV invisible largely. You have some absorption here, right? Kind of that kind of thing. Atmospheric absorption, right? And then you get atmospheric absorption once it hits the Earth's surface and is emitted back out in the lower, or the larger wavelengths. So in the infrared and beyond. And we know that we're not a bare rock, you know, planet with just a simple atmosphere like Mars or whatnot. We have these particles in our atmosphere. We have these properties in our atmosphere like water and carbon dioxide and oxygen and ozone and methane and nitrous oxide and all kinds of stuff, right? And each of those have a potential for absorbing energy. And remember, we're still not necessarily talking about heat. We're talking about just the absorption of that radiated energy. But we start looking at, okay, so we're broadcasting energy in this wavelengths from the sun. Some of it's absorbed and scattered in the atmosphere, you know, all along here. And look, like the chemistry of the atmosphere is not necessarily absorbing it. Water's picking up a little bit. The ozone absorbs all the really, you know, gnarly stuff, right? This is why in places where we had the hole in the ozone, we had extremely high cancer rates, right? So it's mostly scattering and ozone that's able to kind of filter out that initial stuff. Then we have all that energy that we see and that makes plants grow and all that kind of good stuff, and it tailors off. And as soon as it starts tailoring off, then we re-emit it back off the Earth's surface. And what's really key about this is focusing in on this little part of it. So you have some potential for absorption, certainly over here in the general atmosphere. But the things that are kind of contributing to this general absorption are water vapor and carbon dioxide. That's a big part of it. A little bit in oxygen and ozone, and a little bit in nitrous oxides. All right. But these are what's making this strong absorption right here in the stuff that we emit back off the Earth's surface. So we've absorbed all this. We've kind of converted it into different kinds of energy. We are re-emitting it because we're a closed system, right? In larger wavelengths, but it's being absorbed in the Earth's atmosphere, and specifically because of water vapor and carbon dioxide. This is huge, right? We know things about water and carbon dioxide and the fact that they're dipoles, right? And that they are able to absorb energy and actually trap it as heat. There's this narrow little window that allows this, but it is, right? And so what we know then is because the sun is reflecting in these wavelengths, the Earth's atmosphere is mostly transparent to solar radiation. i.e. we allow most of it in. We're a window, right? But when it comes to stuff that we emit back off of Earth's atmosphere, well, the atmosphere, or off the Earth's surface, the atmosphere is actually relatively opaque. It doesn't allow much to be reflected back off and leave Earth's system and go into outer space. It actually traps a lot of that. And it traps a lot of that with water vapor and carbon dioxide. This is why carbon dioxide is focused on so much as a greenhouse gas and less so on those other greenhouse gases because it's just so much a part of that Earth's emitted radiation. So now we have an idealized perfect greenhouse then, where we do have this incoming radiation. We still have radiation going out that's immediately affected. We have this absorbed stuff. We have the emitted, but we also have the stored energy. Now we have a thermal component that's stored in the clouds or in the Earth's atmosphere. We have an energy component. And if we assumed that all of it was stored, well, then we'd have an Earth that, had no glaciers or whatever, right? And that's obviously not the case either. So we're not a bare rock Earth, and we're not a perfect greenhouse Earth. We're actually somewhere in between, right? We are something more like this, because what we have is an Earth's surface that behaves differently when you heat it up. And when you have different surfaces acting differently, you get these thermal differentials. This causes convection. Convection means you get the air moving around, right? So you causes air near the surface to warm and rise, and this causes sensible and latent heat transfer from the Earth's surface to the higher levels of the atmosphere. So now you've got you got sun coming in, some of it's bounced off, but most of it's still making it in, 2/3 of it's making it in. We're absorbing it, we're re-emitting it in certain wavelengths. Our greenhouse gases are capturing those, thus warming up sort of the overall atmosphere. At the same time, the Earth's surface then is heating up, creating more latent and sensible heat via convection, meaning we're just in this feedback cycle that is increasing the warmth, the warming. And this is kind of where we're at right now. This is our conceptual understanding. This is our budget that we've got worked out so far. Is these components, we understand most of it's coming from the sun, but the stuff that's being re-emitted off the Earth's surface is actually more potent for temperatures, for heat transfer, heat storage within the Earth's system itself, atmosphere itself. The way I actually understand these relative contributions, these numbers are not super important, trust me, for this class. If we were going to go and model climates, then we'd really want to dig into these watts per meters cubed, but we don't have to worry about that right now. Just look at the relative kind of contributions of both the sun coming in and the fact that we absorb and emit and radiate and everything. And all that creates these weather patterns and things that tend to contribute to overall, long-term climate systems. So that's where we're at. That's kind of the basics of the energy budget, and we'll go a lot more into the next steps of sort of the some of the other equations and considerations in the next lecture, and the lab this week, or not the lab, sorry, the exercise, the in-class exercise, is really going to be kind of playing with what happens when you add a little bit of this and a little bit of that. Like, what kind of planet do you have? Let's play chemistry lab without atmosphere, and let's see what we have to just really grasp this notion of a budget.